Okay, go ahead.
Okay, sorry about that. So I'll try to race through my sheets because I have way too many. Today I'll talk about gravitational waves. So we're a little bit a new kid on the block in the astronomy community, and then how we used Python for detecting those. So really quickly about myself. So I'm not an astronomer. I don't know a lot about software, but I have a background in experimental optics. After I did my PhD, I worked for the last 11 years. I worked at the site of the Virgo Interferometer on the commissioning and the fine-tuning of the instrument. And only recently I moved to the NICAF group in Amsterdam, but I'm still continuing doing the same work. So I do have a long experience with MATLAB and a little bit less with Python. And although I do use a lot of open source software, I didn't contribute a lot myself, except for the scipy.constants, which I wrote when I should have been writing my thesis. So really quickly about gravitational waves, if you really haven't been following the news the last few years. So gravitational waves are just a natural solution to general relativity. Those are waves, and they propagate with the speed of light. And what they do is they stretch whole of space-time in two orthogonal directions, orthogonal to the direction of travel. So you see that here is shown as an ellipse of free-falling masses, which are initially in a circle, but they're stretched to an ellipse, and half a period later, the ellipse is stretched in the other way. So the way we describe this always is by talking about the gravitational wave strain, and that's simply a delta L over L. And these signals are generated when you move around really heavy masses in non-symmetric ways. And these signals are typically extremely weak, so we're talking about 10 to the minus 21 for typical sources. So how do you do this? How do you detect this kind of waves? We do that with a variant of a Michelson Interferometer. So that is shown in this little cartoon. So if you imagine that the two end mirrors of your Michelson Interferometer are these free-floating test masses, you see that the arm lengths of your Michelson, they stretch in a differential way, and that is exactly what a Michelson Interferometer measures. So in practice, this is a little bit more complicated. So we use all kinds of optical and mechanical tricks to get this really high sensitivity that we need. The thing we measure with interferometers is actually the amplitude of a field, and this is not like a telescope that you're pointing in a single direction, but it's omnidirectional. But we do have an antenna pattern. And if you'd like to know more about this, just talk to me in the coffee break afterwards, because I don't have time to explain this. So there's many facilities around the world that try to do this, and they've been working on this for the last 40 years or so. The three main ones at the moment are the two LIGO detectors in the United States, and the third big one is the Virgo Interferometer in Italy, and that's so the rest of my talk mainly focuses on this one because I know that best. So after many years of working on these machines, you likely heard about 2 years ago the two LIGO interferometers, they were online and they measured their first detection, and this was an in-spiral of two intermediate mass black holes. And I think Duncan already showed this plots 1 year ago, so unfortunately I cannot talk a lot more about this. So at the time, the Virgo Interferometer was still switched off, and we were doing our best to finish our upgrades. And after struggling for a long time, we finally came online in August of last year. And only 2 weeks later, we finally did our first detection together with LIGO. And it's shown here in this graph. So because our sensitivity was still a little bit lower, so we saw it with pretty low SNR, but still it's a real signal. Again, this type of signal was a black hole in spiral. Then what's the real advantage of having more than two detectors? That's actually because with that you can do a triangulation of the location of the source on the sky. And you see that here in the sky map shown here on the top right. So the big bananas, that's what LIGO measured by itself by using just two detectors. And so for this first detection where we could measure something with three interferometers at the same time, you see that the area on the sky collapses a lot. And this is, of course, really interesting to do follow-up measurements with telescopes. Just there's one little detail, and that's that black holes are actually pretty boring for telescopes because it's just singularities in space-time. So at Virgo, we were already extremely happy that we did our first detections, and we said for us we can now switch off and then continue doing our upgrade. But there was actually more, and it was only 3 days later. And that is when we've, for the first time, detected the in-spiral not of two black holes, but a pair of neutron stars. And these are astrophysically much more interesting. And the signal of it is in-spiral because these masses are much lighter. It actually took almost 30. It was visible for the last 30 seconds in our bandwidth. And if you make some sort of spectrogram, you see this typical chirp. So of the two bodies in-spiraling, going faster and faster and faster until they finally collapse. Even that was not everything, because just 2 seconds later, some of the gamma ray telescopes they saw a gravitational wave of a gamma ray burst. So when you have multiple detectors, you can do sky localization. And it was a bit sad for us that for this detection, Virgo actually didn't measure almost nothing. And that was partially because we had a little bit lower sensitivity, but part of the reason was that interferometers have blind spots. And we didn't see it because it was actually located in one of the blind spots. And surprisingly, this helps in your sky localization. So if you put all this data in your algorithm, what you see here is indicated by green is what you would have seen if you only would have used the LIGO data. But then if you add the almost non-detection of Virgo, you see that the sky location actually shrinks by quite a lot. So the sky location was sent to the telescopes, and then only several hours later, when it became dark in Chile, some of the small robotic telescopes they actually could measure, they could find an optical transient on the sky. So this was sent then to all the big telescopes, and you probably know more about this than me, but this was probably the astronomical event that was detected by the most telescopes at the same time. And so there's tons of really interesting astrophysics and even fundamental physics, like measuring Hubble constants, ruling out some crazy theories about dark matter and so. And unfortunately, also here I cannot go more into detail. So this is all of this is really nice, but what does this have to do with Python? Now, for myself, the use of Python started a little bit with throwaway scripts. So what we typically do when we're working with the interferometer, you do a measurement, you write a 50-line script to do some really quick and dirty signal analysis. You make some plots, you make a logbook entry, and you forget about your script. And so in our case, we were typically, most people were typically using MATLAB. And when you do this kind of plots multiple times, you start building your own library of little tools, because you don't want to reuse everything at the same time. So I had my own collection of these tools, which then later on were used by several other people. If you've ever used MATLAB, you know it's really nice for data crunching, but it's not so good for almost everything else. So slowly, over the years, I started converting some of these tools to Python, and then also I started adding more functions to actually control the hardware of our machine. And only later on, I found out that also at LIGO they started building this kind of tools, and the nicest one of those is called GWPy. It's made by Duncan, and so I hope actually in the next few days to hack a little bit on that and start making his tool more compatible with the Virgo data, so that I can drop support for some of my functions and only keep the really interesting stuff. So the type of work we typically try to do in the commissioning work is trying to understand the noise of our interferometer. So typically we make this kind of plots. This is the amplitude spectral density over strain sensitivity, and the scale on the y-axis is 10 to the minus 23. So this is how it looks in the ideal case when you're only limited by shot noise, quantum noise, seismic noise, and so. Unfortunately, in reality, it typically looks more than this. So you have all kinds of experimental artifacts, noisy machines, and it takes many years of commissioning to understand all of these and mitigate all these issues. So the problem is in this is that this kind of machines are extremely complex. So typically we were looking at several thousand of fast channels, which record at something like 10 kilohertz. And in some cases, almost 100,000 slow channels, like temperature sensors and so. So if you have a problem and it's observable in one of those channels, how do you find this needle in a haystack? So one of the tricks I've been doing, and also several others, is to make some sort of brute force tools to find this kind of to automatically find this kind of problems. So there's several examples for this of this, and then they work in different ways. So and then the first one, for example, looks at coherences. So you have one target channel, which is your gravitational wave signal, and you start to doing a coherence with all of these 1,000 auxiliary channels, and then for every frequency bin, you're trying to you make a ranking, like which channel has the highest coherence in this frequency bin. And for example, if you have a nasty peak at, for example, 45 hertz, due to some fan of a piece of electronics, which is spoiling your sensitivity, then hopefully somewhere in your instrument you have a microphone which measures the sound of that. And by doing a correlation between this microphone and your gravitational wave signal, you might find out that this noise comes from something located really close to this microphone. And this is the way how we do find some of these issues. We don't look in this only in the spectral domain, but also in the time domain. So in some cases we find that the certain sensitivity or in a certain bandwidth correlates, for example, with the temperature of an air conditioning system, and that's because this air conditioning machine is making a lot of noise. So these are two examples of something done by a colleague of mine at Caltech. The last example is something I built myself, and that's something that looks at transients. So we have lots of experimental glitches which can mimic a gravitational wave signal, and obviously we want to get rid of all of those. And we already had tools to look between correlations between glitches in the main channel and in the auxiliary channel, but we found out that there's also correlations between the time of a glitch and the value of a certain auxiliary channel. And the way I did this was to look at to use some sort of histograms to again make a ranking of channels. Then a little bit about the automation. So these machines are enormous, really large in scale, but also really complex. So you need some sort of industrial automation system. You also have a really complex sequence of events that we need to do to start up this machine. So typically, when the machine is switched off, all the mirrors they're freely swinging. But when we want to measure, we need to keep everything controlled with picometer accuracy. And so to do this startup, we have an automatic procedure which takes about 10 minutes. And then during this time, we need to switch flip many switches, change gains, offsets, things like that. So historically, they were doing this at LIGO using Perl scripts. If you think that's bad, at Virgo, we developed our own scripting language, which was really nice. It had really nice interface with our data acquisition system, but it was bad for everything else. So we tried and did some early tests with MATLAB, but wouldn't it be nice if we could use a nice language like Python, for example? So we asked this to our software guys and said, yeah, we look into it, but they never did anything. So in the end, me and one of our software engineers, we started playing a little bit ourselves, and the big breakthrough came when we started, when the other guy, he found a way to automatically wrap or use proprietary C libraries, and there's something called C-types gen. It's a little bit abandonware, unfortunately, but it was working reasonably enough. Then there's other parts of the machine which use a more open source framework, and it's called Tango, and in that case, the interface with Python was already existing. And in other cases, when we buy new hardware, sometimes there is no interface, but then you read the manual and you see it has some telnet interface, and you do some quick hacking, and then you can also talk to that. This I think I'll probably skip, but the takeaway of this is that our whole machine consists of hard real-time loops, on top of which there's slower loops which run at maybe 1 hertz, and on top of which there's even a slower loop, which is the operator, which looks at screens and so. So we have a hard real-time loop which controls the mirrors, and then slower loops, and an operator. And what we're trying to use Python for is now only this slower part. So obviously the hard real-time stuff we cannot use Python for. The way we do that, and especially this log acquisition, is by using a system of state machines. It was something developed at LIGO. So it's a hierarchy of state machines. So on top you have the master node, where you can really say from everything switched off to go to science mode, and in the ideal case, it's just one click of the button. And this top node then commands several other nodes which are running at a lower level. And each of these nodes is a little state machine with many states, from switched off to going to several different states. And each of these states in the node is defined by a really simple Python class. So this is something typically programmed by the end user. And it's really like a tiny Arduino program where you do something once, and then you do something in a loop where you check, for example, if a power arrived at a certain value. Or you can also do safety checks, like in case there's an earthquake coming by which unlocks our machine. You can detect that and then switch off everything in a safe way. And so this was already used by LIGO, and so this was had been tested for several years, and was working really well. And since at Virgo we already could control everything by Python, we were able to reuse this software in a pretty short time. And I'm convinced that this saved us many months of commissioning time, and this commissioning time is extremely expensive for this kind of machines. Then really quickly about some other parts of the machine. So I don't know myself a lot about the data analysis, but when our machine is running, the whole output of our machine is just a stream in the time domain of probably at 10 kilohertz or 4 kilohertz of time domain strain data. This is fed to several data analysis pipelines in parallel. And some of the two main ones they're called PyCBC, which stands for Compact Binary Coalescence. And there's another one which is based on the open source GStreamer framework. And what they basically do is take all the signals, and then they do a sort of matched filtering. So they convolute the data with known templates, which are calculated using GR. And then you try to find, for a certain parameter point in your parameter space, you try to see if a gravitational wave signal with those parameters is present in your data. So these programs are extremely complex. So they do lots of statistical analysis, and this is parallel computing. So typically we spend millions of CPU hours to do such analysis, and all of this is written in Python. If you want to play with a little bit more with this data yourself, so that there are examples in our open source in our open data center. And then we also do low latency follow-up. So when we detect something, we try to send this to our telescopes, and also all of that is done in Python. And finally, we use Python for many things like visualization, and recently also more for building graphical user interfaces. Even we started using it more and more for also optical simulations and optical design. So yeah, to conclude, so after many years of working on gravitational waves, we finally made our first detections. It was first done by LIGO, and it was a set of binary black holes. More recently, we also measured a pair of neutron stars, and this really started the era of multi-messenger astronomy. And Python has played a big role in all of this. And this started small, but we're using it more and more. So the type of work we did so far is not a really good example of how you should write nice software. So this was basically an ugly hack done by people with too few people and too few time. And so it's my conviction that while using Python, we managed to save many months. And if we hadn't used that at Virgo, we would have been too late to join the O2 science run, which would have meant that LIGO would have switched off because they were waiting for us, which would have meant that they wouldn't have detected the kilonova. That's it.
Awesome, thank you. Any quick questions? Yes, Stuart, come up and we can start getting set up. So, I mean, I think that a lot of projects start off as quick hack together. Are there hopes to kind of pull things together into something more uniform? It seems like it's happening slowly.
We're trying, but we're always short on time and short on people. But we're doing more effort now to use unit testing. We're trying to move to Python 3 in the next year or so, using more version control for everything. And so we're trying, but it's hard. So
baby steps and best practices. Awesome.